Andrew Braham is Associate Professor of Civil Engineering at the University of Arkansas. He developed online training and certification for asphalt emulsions and is active with PPRA and AEMA. Andrew is also active in TRB and a member of the Pavement Preservation Technical Committee. Andrew Braham, present on manufacturing.
Thank you very much for having me today. I appreciate the opportunity. As it was mentioned, I'll be talking a little bit about manufacturing of asphalt emulsion. Now, if we were in person, this would be slightly more entertaining because I like watching people as I talk. Sitting in a classroom, I realize fully how many distractions there are. So I'm going to start out with something a little fun that has absolutely nothing to do with manufacturing of asphalt emulsion. And that's a thank you to Judy. And if she was in the room right now with us, you'd see her rolling her eyes. But I was fortunate to first meet Judy when she was the committee chair for AHD 18, which is the Pavement Preservation Committee. And if everyone can close their eyes and remember a time where we could all come together in person and actually talk to each other, this is one of those events. That was in 2018. And she's on the left there diligently running the meeting. And then I'm on the far right watching Stacy Williams, Dr. Stacy Williams, give a presentation. But this is where we first met, and I've been privileged to work with her in several other places. And for those of you who don't know, she's actually stepping down from her role as director, but has assured me she'll stay involved with TRB. So I look forward to continuing to work with her in the future. So thank you very much, Judy, for everything you've done for our community. Now, getting back to manufacturing of asphalt emulsion, this is a general plant layout. So this complements the slide that we saw Chris Lubber's presentation present. He showed a schematic of an asphalt emulsion manufacturing facility, and this is a little more broken down into the base components. And you can see along the top, we have storage, we have transfer, we have the milling of the asphalt emulsion, we have the transfer, and then we have storage again. And what we're going to do is we're going to walk through the storage, the transfer, and the milling process for asphalt emulsion in this presentation. A brief overview for storage: we need to store the asphalt binder. We may need to store water. We definitely need to store emulsifiers and chemicals, and then the asphalt emulsion itself. So you have the raw materials there on the front, and then the asphalt emulsion, that's the finished product, on the back. And in this storage, we need to have some sort of tanks or holding facilities. We need to provide heat, and we need to have insulation. And if you ever have the opportunity to go to an asphalt emulsion manufacturing facility, I highly recommend you do. They're fascinating places. The vast majority of space is taken for storage, but it's all connected by these transfer mechanisms. And again, you need to transfer all the raw materials, the asphalt binder, the water, the emulsifiers, and the chemicals, and then you need to transfer the asphalt emulsion. And this is done using pipes, meters, pumps, valves, and static mixers. So those are all the devices that go along with the physical transferring of these materials. And you also have strainers, but I put those on a separate line because you never want to strain asphalt emulsion. If you recall, Chris had that nice slide with the particle size of asphalt emulsions, and you never want to strain it because it will impact that particle size and it could damage the asphalt emulsion itself. And then finally, where all the magic happens, the asphalt emulsion mill. This is where you take the asphalt binder and the soap solution and you shear the asphalt binder into small droplets, and then the emulsifier surrounds the binder droplets, and that's what creates the asphalt emulsion. So this is a broad overview, and let's dig into each of these categories a little more, just to get a basic understanding of each one of these components. So let's start with the storage. We're going to talk about asphalt binder, we're going to talk about water, the chemicals and emulsifiers, and then the storage of the asphalt emulsion itself. When we're talking about asphalt binder storage, if you recall from CJ's presentation, he spent a lot of time describing modified asphalt binder, polymer modified asphalt binder, and this asphalt binder can be polymer modified if you're interested, or you can also use neat or unmodified asphalt binder, but it's usually the largest storage facility on an emulsion plant site. And that's because usually there's not a whole lot of different types that are being stored. Each binder type can be used in multiple asphalt emulsion grades. So there's maybe 3, 4, 5, sometimes more, but usually just a handful of different asphalt binder types that are being used in a facility, in a medium-sized facility. So you can generally store those in larger tanks, and there's fewer of those tanks compared to other materials. Now, the tanks themselves are usually made of carbon steel, and they can be anywhere from 5,000 to 60,000 plus gallons. The one on the right there, that's one of those 60,000 plus gallons, one of the big ones. And the tank itself is actually composed of three parts. It has a bottom, it has a shell, and a top. And those are all designed to act together as a unit, but then they all have their special features. And the tank walls actually get thinner as you go up. And that makes sense because you have less pressure toward the top because there's less head pressure of the material within the tank. And then finally, a very important component is you do want a pressure release at top. And that's because when you're filling the tanks, you want air to be able to escape. When you're emptying the tanks, you want air to be able to come in. You don't want those tanks to collapse or have the top pop off on you. Now, water storage, this isn't talked about too often, and that's because water is usually obtained directly from either a city or some sort of local agency, and it's usually just accessed when necessary. It's like turning a faucet on in a sink, but it's just a really big faucet and a really big sink. So often no tank is necessary to store water. The only exception, the only common exception to that is if you are making an anionic asphalt emulsion, because anionic asphalt emulsions do require soft water. So if your area has hard water, you will need a tank. You need to heat that water up to about 160 degrees Fahrenheit, and then you add some sodium chloride, and that softens the water through an ion exchange. Now, for emulsifier and chemical storage, this is usually the smallest storage facilities in the asphalt emulsion manufacturing area, and that's because these emulsifiers and various chemicals take up less than 5% by weight of the asphalt emulsion. And usually you store these emulsifiers or chemicals in either high density polyethylene, HDPE, or some sort of fiber reinforced plastic. And there are three types. So you have your typical 55-gallon drum that you can bring these emulsifiers and chemicals in, and they're mobile. The picture on the right, you can see a tote, and this is about 275 to 330 gallons, depending on the type. That is also mobile. You can move that around with a forklift. But then you also have tanks. So if you use one type of emulsifier or one type of chemical, for example, cationic asphalt emulsions often use hydrochloric acid or HCl as an additional chemical. So if you make a lot of cationic asphalt emulsions, you may have a tank of hydrochloric acid on site. Now, because it's not used in a lot of quantity, they're usually less than 5,000 gallon tanks, so relatively small, but those are permanent. You're not going to move those around. Now for the asphalt emulsion storage, this varies greatly. The temperature varies greatly on the grade of asphalt emulsion, and I'm not going to get into those details, but a couple rules of thumb. You never want the temperature to go above 185 degrees Fahrenheit. That's because you're starting to get close to the boiling temperature of water. And asphalt emulsion is 33% water. So if you boil asphalt emulsion, you'll boil the water and you'll just have the asphalt binder left and you'll lose your asphalt emulsion and you can't just put the water back. And there's similar principles when you get near freezing. You never want to go below 50 degrees Fahrenheit. And again, that's because you're approaching the freezing temperature of water, and your asphalt emulsion will also be destroyed if you freeze your asphalt emulsion, and you can't just get it back by thawing it. You want to avoid horizontal tanks. You want to use a vertical tank like the image on the right, and that's just because of the surface area. Sometimes a skin forms on the asphalt emulsion, and that's just because the water is evaporating at the top of the tank, and so you have a smaller surface area with horizontal tanks, a smaller surface area of exposed asphalt emulsion. It's generally good practice to have paddles in these tanks, and you want to give it a very gentle stir every 2 to 3 days. And these are very high torque paddles, low speed. You don't want to inject air into there to, try and circulate it roughly. You want to be very gentle with your asphalt emulsion, or else you could damage it. And then Chris also spent some time talking about charges and reactivity of asphalt emulsion. So you want to make sure that you use designated tanks for asphalt emulsion. So you want cationic asphalt emulsions going into cationic tanks. So you want that charge to match. You want anionic emulsions going to anionic tanks. You want those charges to match. And if I was standing in front of you right now, I'd ask everyone to raise their hand. And I'd ask the question, what would happen if you mix two differently charged asphalt emulsions? And the answer is you'll have a very unhappy plant manager and a completely ruined tank of slop. So you don't want to mix charges. Now you can mix reactivities, but you do want to take care if you put a higher reactive emulsion into a tank. So you want to be very careful putting, for example, a CRS into a tank that had CSS, because the CRS is a more sensitive emulsion. It'll break more quickly. You can go the other way with relative ease, but again, you just want to be really careful about mixing different types of asphalt emulsions. Always err on the side of caution before just trying something out for fun, because these are thousands of gallons of asphalt emulsion, and it's a pretty big mess if there's some sort of problem. Another very important part of all types of storage is spill containment. You want to make sure that your entire manufacturing facility is surrounded by a spill containment, and that containment needs to hold the volume of 110% of your largest tank size. And that's so if your largest tank gets a hole in the bottom of it and completely drains, it can fit within your spill containment. And this can be anything from an earth berm to a concrete wall. Again, if you go to a different emulsion facility, they all are slightly different, but you want to make sure you're able to contain any sort of spill if a tank does happen to get a hole in it. Now, all tanks need some sort of heating and insulation. So heat sources can come either from steam or hot oil. And you want to make sure that this steam and hot oil has completely separate piping and metering systems than any of the asphalt emulsion or raw materials going into the asphalt emulsion. So when you're walking around a plant, there's actually two completely separate sets of pipes. And that's because one has to do with the asphalt emulsion and one has to do with the heat, whether it's steam or hot oil. Tanks generally have coils at the bottom, and that's another reason why you want to be able to stir the asphalt emulsion, or you can recirculate the asphalt binder through pipes. Those coils at the bottom are the heat source, so you don't want just the bottom getting heated. You want it to be a homogeneous temperature throughout the entire tank. Now, asphalt binder, depending on the grade and whether or not it's polymer modified, as CJ was talking about, it can be anywhere from 200 to 390 degrees Fahrenheit. The emulsifier is anywhere from 120 to 200 degrees Fahrenheit, and emulsion is anywhere from 50 to 185 degrees Fahrenheit. Now you can also see on the exterior of the pipes shown in this picture, there is some insulation, and the insulation can be mineral wool, it can be glass wool, rigid foam, or polyethylene. So lots of different options there. And you want to have this insulation around the heated tanks and the heated pipes, and that just traps it, it saves some energy, and it makes for a higher quality product going through your plant. This heat and insulation, it prevents the freezing, it reduces the energy needs. Another big thing is it keeps your viscosity constant, because as temperatures change in all these materials, the viscosity changes, and that will change how it pumps through the plant. It can stabilize temperature, and then finally it increases safety, because I don't know about you, but I wouldn't want to touch an asphalt binder tank that's 390 degrees Fahrenheit. If you do ever tour an asphalt emulsion plant, just don't casually lean against anything anyway. But if you do happen to brush up against something, you don't want to get burned or anything. So you got some increased safety there as well. So we're moving in on the general plant layout. We've kind of covered the basics of storage. Now we're going to talk about some of the basics of transfer devices. So let's start with pipes. For asphalt binder, you want to use ungalvanized steel, and these are generally the largest pipes. They're anywhere from 8 to 12 inches in diameter. For the water that you're pumping around, you want to use galvanized steel, and you generally have 4 to 6 inches in diameter. For emulsifiers and chemicals, you generally use either some sort of flexible plastic or rubber or some other plastic or rubber pipe, usually 2 to 4 inches in diameter. And you can see these diameters are related to the approximate percentage of materials in there. Now, when you add the water, the emulsifiers, and the chemicals all together, you have to go through a certain sequence of that. You get what's called a soap solution. And soap solutions usually use polyvinyl chloride pipes, and they're anywhere from 2 to 6 inches in diameter. Now, just like the tanks, it's very important to clean these pipes, especially if you're switching material. And pipes get a little tricky because there are a lot of shared use pipes in a plant. Tanks tend to be a little more siloed, literally and figuratively. But pipes, they all kind of go together to the same place. They all go from the raw material storages to the mill, and then from the mill to the emulsion tanks. So you do want to make sure you're diligent about cleaning your pipes. With asphalt binder, you can either blow pipes with air or you can flush it with solvent. With the emulsifier and the chemical lines, you can blow them with air or you can flush them with warm water. And then for the soap lines, you can blow them with air or you can flush them with either warm water or a soap solution, which can be diluted. So lots of options there. But at the end of the day, these pipes are just moving material around the plant, and you need to make sure you're taking care of them. Now, meters are very important because you need to know what's going on in those pipes. So the first meter of importance is for temperature, and it's not only important for pipes, but also for tanks. So you can measure the temperature in a tank itself, you can measure it along a pipe, and it can either be an analog or a digital temperature thermometer. I tend to be a little more old school, so I threw a picture of an analog thermometer up here. I just think it's so much easier. These don't break when the electricity goes down or anything. They're pretty handy. For the flow rate, if you want to try and measure it in a tank, you can use a tank level board. So if you look at a tank in an asphalt emulsion facility, there's a tank level board on the side, and that's generally a big ruler. And that ruler says how much material is in that tank. And if you watch that ruler dropping or rising, so if material's either leaving or going into a tank and you time it, you can get a general flow rate. But there's a lot more accurate ways to capture that, and that includes a Coriolis or split flow meter for flow rate. You can have electromagnetic flow rates, and you can have mechanical spring-based meters to measure the flow rate. Finally, the last meter that we'll cover, there's obviously many more smaller meters, but these are the big three: the temperature, the flow rate, and the pressure. You can measure pressure along a pipe, and this is done with a static pressure probe. And also there's often a pressure gauge right at the mill because sometimes you need to apply some back pressure. And that's a little teaser for a future slide in this presentation. Regardless of which meter you're using though, you wanna make sure that the design of that meter is followed. You can't just toss any old meter anywhere. You wanna make sure you're following the installation and use guidelines to make sure you're getting an accurate result. Because you can measure something and it might give you a number, but you wanna make sure it's accurate so you can make a high quality product. Something's gotta move this material around, and those are pumps. So for asphalt binder, you usually use a positive displacement pump, and a gear pump is the most common. And they're usually 30 to 35 horsepower, and you wanna make sure those are insulated because your asphalt binder needs to be kept hot at all stages. You don't want to cooling off in the pump because then you'll just have a gummed up pump. For emulsifiers and chemicals, they also use a positive displacement pump. They usually use a diaphragm pump, and you can see a picture of a diaphragm pump on the right. These are generally 5 to 10 horsepower. And then for soap, you also use a positive displacement. You can either use a diaphragm pump for positive displacement, or you can use a kinetic pump, a centrifugal pump as well. So a couple different options there, and those are usually around 20 horse. Now for positive displacement pumps, that means you have a fixed volume discharge. So there's some sort of volume that gets chugged out every time period. It can be every second, every 5 seconds, every minute, whatever it is. And kinetic pumps use fluid static pressure in order to move the materials. Whichever way you go though, the whole point is to move materials along the pipes. The rest of the transfer devices for valves, there's 3 types of valves you can have. You can have a shutoff valve, and these are either on or off. There's no in between. It's binary, black and white, shut on or off. You can have throttle pumps, and this can control the flow. So a throttle pump, you can usually turn at some sort of angle, so you can have anywhere between completely on to completely off, or you can have about 45% flow. You'll often see those around mills also to control the flow going into the mill. And then you can have what's called a check valve. And check valves are really nice because they force fluids to move in one direction. Like for example, you never want asphalt emulsion going from a tank back to the mill. So there's often a check valve there that prevents any material going into the mill from the mill discharge. And there's various other locations for a check valve as well in a plant. You can also have static mixers you only use on raw materials. So you only use it on the asphalt binder, the soap solution, the chemicals, the emulsifiers. You do not use a static mixer on asphalt emulsion. That'd be a great way to damage your asphalt emulsion. And you either have a static mixer just after that raw material tank or just before the mill. Kind of depends on the type of setup you have. And I'm going to get to that in a second as well. And then you also want to have strainers. So strainers can be beneficial for batch plants, but they're required for continuous plants. So you can see the picture on the left that shows a piping system, and that is a strainer in the middle of that picture, or with the little sample pipe coming off the bottom of it. That's where the strainer is. And if you'd open that up and take the strainer out, that's what it looks like on the right. But that keeps clumps from going through. If there's any sort of debris in your tanks, it keeps those from going in to the asphalt emulsion mill, and it just provides a more homogeneous product going through your plant. Now, there's only one piece of equipment left that we're going to talk about, and that is the asphalt emulsion mill itself. So we've talked about the storage, we've talked about the transfer, and now we're honing in right on the middle there on the asphalt emulsion mill. Chris already talked about this a little bit, but the purpose of asphalt emulsion mills is to shear asphalt binder into tiny droplets. And the way that you do this is you embed emulsifier into those droplets. And those suspended emulsifier covered asphalt binder droplets are then suspended in water. So you can see on that picture on the right there, you have droplets of asphalt binder surrounded by emulsifier, and those are suspended in water. And those emulsifier charges act as similarly charged magnets. So if you've ever tried to push two magnets together that have the same charge, they'll do everything they can to prevent getting pushed together. They'll push apart, they'll shear apart. That's the whole thing the emulsifiers are trying to do, is trying to prevent those droplets from joining together. Well, how do we do this in the asphalt emulsion mill? The most common type of mill is a colloid mill, and that has one stationary plate. So the picture on the right, that's the upper right hand plate. That is stationary, it's not moving, and it's called the stator. And then you also have one rotating plate, that's the one in the foreground in that picture, and that's called a rotor. And that rotor rotates and it shears asphalt binder into droplets. So the material comes in through that hole in the center and it gets forced out, it gets sheared between those two plates, and you get your asphalt emulsion. And this can either be a flat plate, which is shown in the picture, or it can be a cone shaped. And if you close your eyes and think of a cone, that's exactly what it looks like. It's two cones that slide into each other, but they have these type of teeth on them to help with that breaking down. So the soap solution in the asphalt binder enters in the center and it exits on the edge, as I mentioned, and the rotors shear the material against the stators, and there are multiple sets of these, and they're going at about 90 feet per second. And this is a shear rate of about 60,000 hertz. So this is an incredibly fast speed, and these plates are fractions of an inch apart. It's very, very, very close together. And so this is what shears the asphalt binder droplets into small particles, and you get your asphalt emulsion. And as it's going through these rotors and stators, that is what forces the emulsifiers out of the soap solution into the asphalt binder droplets. Now I'm just briefly going to go over the steps to manufacturing asphalt emulsion. If you're in a batch plant, what you're going to do is you're going to heat all those raw materials and ensure that they're homogeneous. You want to produce your soap solution, and you want to begin your soap flow through the mill. Then you increase the asphalt binder into the mill until you hit your residue target. So if you're aiming for 66% asphalt emulsion or asphalt binder residue in your asphalt emulsion, you just slowly dial it up until you hit that 66%, and then you're good to go. When you're done making your run, you flush the mill with the remaining soap to clean it out, and then you can make your next product in a batch plant. A continuous plant's a little different. Instead of making the soap solution in a tank, you make it in the pipe and you make it on the fly. So you have your chemical, your emulsifier, and your water. You add those all together in a pipe and it goes through a static mixer, and that makes the soap solution. And if you do this in a batch plant, it goes into a tank. If you do it in a continuous plant, it goes into the pipe and then directly into the mill. So you don't actually have a tank of soap solution in a continuous plant. And it's nice because you can modify things during production. If your asphalt emulsion isn't behaving quite as you'd like, you can tweak your chemical, you can tweak your emulsifier, and you can actually modify it as you're producing. However, it requires more instrumentation, a lot more meters. It's a little more expensive, but a lot of plants are moving in the direction of continuous plants. Historically, most have been batch plants. Regardless of if you're using a batch or a continuous plant, however, the meters and the pressure are absolutely critical. So you want to make sure that you're taking accurate temperatures, flow rates, and pressures, and then you are actually applying the proper pressure when you're making the asphalt emulsion. Now, why are temperature and back pressure so important? Well, the temperature of the asphalt emulsion is key, and it's based on the temperature of the asphalt binder and the temperature of the soap solution. And I apologize, but I am going to show one equation. So here we go. Here's your one equation. So if you want to take a picture of the screen, maybe solve some problems on your own. But the asphalt emulsion temperature can be calculated by multiplying the percent asphalt binder by the temperature of the asphalt binder times 1/2. You add that to the percent soap solution times the soap temperature, and you divide it by the percent asphalt binder times 1/2 plus the percent soap solution. And this is important because the temperature of the asphalt binder is critical to get the right viscosity. The temperature of the soap solution is critical because that feeds into the temperature of the asphalt emulsion. And you want to hit that proper temperature of asphalt emulsion to make sure you have a good product. Now, I've kind of danced around the topic of back pressure throughout this whole presentation. Back pressure can be used for two reasons. One, it can increase the time the material is in the mill, which will cause it to shear more, and it'll get that good particle size distribution that Chris showed on his slide. Now, you can also make asphalt emulsion at temperatures greater than 212 degrees Fahrenheit. And if you recall, 212 degrees Fahrenheit is the boiling point of water. In theory, you don't want to have those temperatures because your water will start boiling unless you put back pressure on. So here's a nice little table, and I got this out of the asphalt emulsion electronic circular that TRP put out a while back. But you can see here that at 212 degrees Fahrenheit, you want to have 4 psi of back pressure, and that will allow you to produce asphalt emulsion. And you can actually go all the way up to 275 degrees Fahrenheit, but you got to put 37 psi of back pressure on there. Now, if you do this, you have to put your asphalt emulsion through a cooling tower, or else your water is going to boil, and then you'll have problems. You may ask, are we done? And the answer is no, because I do want to just mention quality control briefly. Quality control is so important. You have consistency testing, and this is found in AASHTO M140, M208, and M316. That covers anionic, cationic, and polymer modified asphalt emulsions. This is a very important part of quality control. This is where you measure things like viscosity, sieve, residue, penetration, and these are materials or properties that you can check while you're in the field. So if you're agencies, these are the type of things you want to track to make sure that you're getting the product that you ordered. Specification compliance is another important part of quality control, and this has to do with pavement. It's very similar to consistency testing, but it's based on the frequency, and you want to check the material that's being stored in the plant. So ideally, you want to store material as minimally as possible in the plant. You don't want asphalt emulsion sitting in a tank for long periods of time, but you can do tests on that plant storage in order to make sure the product is behaving as it should. And then during milling and internal type testing, you can do a quick sieve. This is literally running the asphalt emulsion over a window screen just to see if any large balls of asphalt binder exist. And then you can also run asphalt emulsion residue tests, which is that picture on the right. And that's just a boil off to make sure you have the proper amount of asphalt binder in your asphalt emulsion. And these are things you can check during manufacturing. Now, I'm not going to get into this, but transportation to the field is also critical, and maybe Phil will talk a little bit about that. Don't mean to put him on the spot because he's going to talk about handling and lay down in a couple presentations. So I appreciate you joining me today. If you have any questions, feel free to put them in the chat box. You can shoot me an email right there, and I'd be happy to answer them. But thank you very much. I appreciate it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.